Swayam Prabha. Digital India. Educated India.
So, welcome back to lectures on advanced calculus for engineers. This is lecture number 15 and we will be talking on the composite and the homogeneous functions in this lecture. So, in particular we will be looking at how to find the derivative of a composite functions and the derivative of functions defined implicitly, that will be a part of these composite functions itself, and then we will go through the derivative of homogeneous functions. Well, so what are composite functions? Suppose we have z is equal to f x y, a function of two variables, and here x is again given a function of t and y is given as a function of t, or it may happen that x is a function of again two variables u and v, and y is again a function of u and v. So, this equation number 1 together with this equation number 2, or this equation number 1 along with equation number 2, whichever is the case, are said to define z. So, to define this function z as composite function of t, and in the second case the composite function of u and v. So, we call this z along with this a composite function of t, or this z along with these x and y we call as composite function of u and v. What is interesting here? So, the z is given as a function of x and y, but then x is a function of t and y is a function of t. So, at the end this z is a function of t alone. That means what is our interest now, that what will be dz over dt, what will be dz over dt for instance, because it is just the ordinary derivative of z with respect to t, because z is varying with respect to t at the end. Z is a function of x and y, but x and y both are functions of only one variable t. So, then at the end this z is also a function of t alone. That means this dz over dt, the ordinary derivative of z with respect to t, makes sense here. And now, how to find out this dz over dt in terms of partial derivatives of this f, because f is a function of x and y. So, that is the main interest of this lecture, and definitely we will be using the idea what we have just gained in the previous lecture on differentiability. So, how to differentiate such composite functions? Let this z f x y possess continuous partial derivatives. So, or we will assume that this function is basically differentiable. Continuous partial derivatives means again this is a sufficient condition for differentiability, and we let this x is equal to phi t and y is equal to psi t, they also possess continuous derivatives. So, they are basically also differentiable. Then we will show that the dz over dt, the derivative of z with respect to t, the ordinary derivative of z with respect to t, we can write down in terms of the partial derivative of z with respect to x, the partial derivative of z with respect to y, and then the ordinary derivative of x, because x is a function of t alone. So, dx over dt and dy over dt. So, this formula, which sometimes we call as chain rule, we will see that how to derive this formula for the derivative of z with respect to t. So, we let that z is a function of x and y, and this x is a function of t and y is a function of psi t. Well, So, having these the composite function, we assume that these are differentiable already z, phi and psi. So, that with that differentiability, since z is differentiable, we can write down delta z as z x delta x, z y delta y. This is the definition of the differentiability which we have learned in the previous lecture. So, if we divide this expression here by delta t, that variation in t. So, what will happen, this delta z over delta t, then this dx delta t, delta y delta t, and here also we have delta x delta t and delta y delta t. And now we let this delta t tends to 0, let delta t tends to 0, or basically this delta x tends to 0, delta y tends to 0, because x is a function of t and y is a function of t, and the variation in the delta t we are letting to 0, that means delta x will also go to 0, delta y will also go to 0. Now, here this delta z over delta t, as this delta t goes to 0, will become the ordinary derivative dz over dt, which we are looking at. Now, this term here delta x delta t will become dx dt. This partial derivative is already there, has nothing to do with delta t to 0. Here also in the second term we will have delta y over delta t will become dy over dt, and since the derivative exists, so these terms are finite, then epsilon 1 and epsilon 2 will make these two terms to 0, as delta x goes to 0, delta y goes to 0. So, what we have, simply we have that formula which we were looking at. So, to get the derivative dz over dt, we have to have the partial derivative, then ordinary derivative of x with respect to t, del z over del y and dy over dt. So, this is the formula which we want to derive. So, this we have already seen that when z is as a composite function of this t here. So, z is a function of x y, x is a function of t, y is a function of t, then this is the result to get the dz over dt. Similarly, there are many other variants of these composite functions, like z we have a function of f x y, where x is a function of u and v, y is a function of u and v, and then our interest is to find this del z over del u and del z over del v. So, a similar results we have here also. So, if we want to get del z over del u, we partially differentiate this with respect to x and del x over del u from here, and then partially differentiate z with respect to y and then del y over del u again from here. And similarly, del z over del v we can get. So, the partial derivative of f with respect to x and del x del v, because with respect to v, then here v will come, and with respect to u, then here the u will come. So, again del z over del y over del u. Similarly, if we have the case that z is a function of x alone and then x is a function of u and v, in that case also we can get del z over del u, because now z is a function of x and x is a function of two variables. So, partial derivative of z with respect to u makes sense now. So, del z over del u. So, absolutely from here del z over del u will be now not del z over del x, but dz over dx and del x over del u. So, only this part will go here, because there is no y component in this f. Similarly, for the del z over del v, dz over dx and del x over del v, because x is a function of two variables. So, the partial symbol will come here. Similarly, we may have the situation that z is equal to f x y and x is a function of three variables u, v and w. In that case also we can compute this partial derivative of z with respect to u, partial derivative of z with respect to v and partial derivative of z with respect to w. So, del z over del u, then similarly del z over del v, del z over del w. Well, just go through the problem here. Z is equal to x y and x is cos t, y is sin t, and we need to find dz over dt. So, z is a function of x and y, x is a function of t and y is a function of t, the first case we had just discussed there. So, dz over dt will be del z over del x, dx dt, del z del y and dy over dt. So, each of them we can compute. So, del z over del x will be just y and dx over dt will be minus sin t, then you have here x and then here you have cos t. So, as a result you have minus sin square t plus cos square t, that is cos 2 t. So, this is what we got from the formula, but the direct also it is possible of course in this simple case. So, z is equal to x y. So, x is cos t and then y is sin t. So, this is directly we have written z in terms of t, this as a function of single variable. So, z is equal to this is half and sin 2 t. So, if we get here dz over dt, it is just the half and then the cos 2 t and into 2. So, the result is cos 2 t, of course, the same as we got with the formula. Let z be a function of x and y, and further it is given that x is e power u plus e power v and y is given as e power minus u plus e power v. So, z is a function of x and y both are functions of u and v. Then we need to show this relation that del z over del u minus del z over del v is equal to this x del z over del x minus del z over del y. So, it is simple, we will just compute del z over del u. So, these partial derivatives and these derivatives. So, once we compute that, we got del z over del x as it is and del x over del u we can get from here. So, it is e power u and then del y over del u will be minus e power minus u. Similarly, del z over del v we can compute and then this difference if we take. So, we can see from here del x del z over del x del z over del x we can take common. So, we have e power u and then minus with this minus sign again it will become plus e power minus v, that is x. So, we are getting here x and then in the similarly in the second case we are getting y, which is the right hand side of the given expression. Well, so this is simple. Once we know this chain rule, this formula, this is easy to evaluate. So, problem number 3, we have del z over del u and del z over del v we want to get. If this z is given as tan inverse x and x is given as e power u and ln v. So, here z is a function of one variable x and x is a function of two variables u and v, and then we want to get this del z over del u and del z over del v, these partial derivatives with respect to u and v. So, del z over del u will be del z over del x and del x over del u as per the formula. So, there will be no other term with respect to y because there is no y there in z. So, here dz over dx we can compute as 1 over 1 plus x square from the tan inverse and del x over del u with respect to u. So, this will be e power u alone. So, here we can just substitute this x as e power u ln u whole square. So, this is the value in terms of u and v. Similarly, del z over del v we can get from this formula and again by substituting this x. So, this is the value in terms of u and v. Now, here in this continuation as an application of this formula, we can also get different formulas for the derivative of a function which are defined explicitly. So, there are two types of functions. So, one is like we can write in terms of y is equal to f x. So, for example, y is equal to x square. So, this is an explicit function of x and explicit function y of x. So, here you give x and then immediately you will get the y. So, because y is written explicitly in terms of x, but there are certain functions, for example, if I write x square plus y square is equal to 1. So, this is not written in terms of like y is equal to some function. So, here y is a function of x, but we have a implicit relation. So, we are talking about this case when a function is written implicitly in terms of these x and y, then how to get the derivative. So, suppose we have the functions of single variable, that means y is a function of x and it is defined implicitly in this form f x comma y is equal to 0. So, some relation of x and y is given equal to 0. It is not defined explicitly as y is a function of x. So, what we let here, let z is equal to f x y and this is equal to 0 of course, and then we get this derivative of z with respect to x. Why we are doing so? Because this f is a function of x and y and we know that the y is a function of x and this x is a function of x, we can just treat it as. So, this is a composite function of x, this z is a composite function of x because here x is anyway given there and y is a function of x. So, this is a composite function of x. If we treat so, we can apply that rule there, that del f over del x and dx over dx plus del f over del y with respect to this and dy over dx. So, with this rule if we go and equal to 0 of course, if we now see here that this dx over x is 1 and then we can get this dy over dx, because we want to get out of this as dy over dx, that how to get this dy over dx. So, from here we can write down dy over dx as minus del f over del x and del f over del y, and naturally this del f over del y is not equal to 0, then we can write this in the division form. So, what is the simplicity here, that once we have this explicit function, we can directly write down dy over dx, just this is the ratio of the partial derivatives with respect to x and with respect to y. If we have functions of two variables, suppose z is a function of x and y and it is written again implicitly as f x y z. So, in that case also we will use the same idea. So, let w is equal to f x y z is equal to 0 and we differentiate with respect to x this. So, dw over dx as per our chain rule, what will be del w over del x will be partial derivative of f with respect to x and dx over dx, then partial derivative of f with respect to y and dy over dx, plus the partial derivative of f with respect to z, and then we have dz or partial derivative del z over del x. So, this is anyway 1, these are independent variables. So, with respect to the same, if we are differentiating, this is 1, and here because these two are independent variables. So, this term will not be there because dy over dx is just 0, they are independent variables, they are not dependent on each other. So, this term will not be there. So, we will get just del f over del x and the last term del f over del z over del x. So, from here we can get directly del z over del x as the ratio of these partial derivatives with respect to x and with respect to z. Similarly, if we differentiate with respect to y, we can get the partial derivative with respect to y as the ratio of these partial derivatives with respect to y and z. So, let us go through one example. So, if z is a function of x and y and this is defined implicitly as x square plus y square plus z square minus some constant equal to 0, and we need to find then del z over del x and del z over del y. So, it is simple, no need to remember all those formulas which I have just mentioned on the previous slide. We can directly differentiate the given implicit relation. So, with respect to x, so if we differentiate here with respect to x, this x square, we know that the result will be 2x, y is an independent variable. So, this will be 0 and here z square will be 2 times z and del z over del x and minus this constant. So, this is equal to 0. So, we can directly just differentiate this. So, we will get 2x, we will get 2z and we will get del z over del x, everything set to 0, and from here we can get del z over del x as minus x over z. Similarly, if we differentiate with respect to y, this time this will become 0, here it is 2y because we are differentiating with respect to y, and then here 2z, and again z is a function of x and y. So, here partial derivative of z with respect to y will come, this is equal to 0. So, 2y and 2z del z over del y equal to 0. So, from here we can get del z over del y is equal to minus y over z. Now, we are coming to the last section of this, it is a homogeneous functions. So, these are also important functions, and their derivatives, there are some direct rules, theorems, we can compute some relationship of those homogeneous functions in the form of derivatives. So, an expression, so what are the homogeneous function? An expression x y is homogeneous of order n. So, the order is defined for these homogeneous functions. So, we call this homogeneous of order n if that function can be expressed in this form x power n f y over x. So, this y over x is important. So, if we can express a given function in this form, we call it a homogeneous function of order n, or sometimes we use this definition also, f x y is said to be homogeneous of order n if it satisfies, you substitute in the first argument as t x, here t y, then this t power n should come out of your function, and then f x y will remain in the product here. Good. So, let us go through some example of homogeneous functions. So, for instance, this is one function f x y, a naught x power n, a 1 x power n minus 1 y, x power n minus 2 y 2, and a n y power n. So, we can realize, so here is the power n, here also n minus 1, but 1 power is there, n minus 2 and 2, this again n. So, everywhere if you sum this power of x and y, it is coming to be 2. So, once you see such a situation, one can immediately bring into that form of the homogeneous and find out the order. So, if we take here x power n out of this expression, what we will see, a naught plus a 1. So, here a 1, x power n is out. So, what is remain here 1 over x. So, basically divide by x and multiply by x there. So, x power n is out, and then we have x there. So, y over x. Similarly, here also we have y over x whole square. We have y over x power n. So, this everything is a function of some y over x, or let us call it g, because f is we have already denoted here f x y. So, this is some function g of y over x, and then this is x power n sitting there in front. So, this is a homogeneous function of order n, homogeneous function of order n. If we have, suppose here square root x plus square root y over y plus x, in this case also here we take square root x and here we take x common, then we have square root y plus x plus 1 y over x plus 1, and in this case, so here we have x power minus half there in the numerator, and this is a function of y over x, because everything is written in terms of y over x. So, this is a function of y over x, and then we have x power minus half. So, this is again a homogeneous function of order minus 1 by 2. So, there is a nice results, the so called Euler's theorem on homogeneous function, which is used for evaluating a certain relation of the derivatives of the homogeneous function. So, suppose z is equal to f x y be homogeneous function of x and y of order n, then this is the result that x into partial derivative with respect to x, y into partial derivative with respect to y is equal to n into z, is equal to n into z. N is the order of that homogeneous function z. So, how this result is coming? So, suppose z is equal to f x y, and since this is a homogeneous function, we can write down as x power n and g of y over x, because it is a homogeneous function. It is given to us that this is a homogeneous function, and then we get the partial derivative with respect to x. So, by taking the partial derivative with respect to x only, so we have first the product rule here. So, n x power n minus 1, the g as it is, then this x power n as it is, and then g prime y over x and the derivative of this y over x, which is minus y over x square. That is the term we can see here. Well, we can simplify a bit. So, n x power n minus 1 g, and here we can have x power n minus 2 into y, g prime y over x. Now, the partial derivative with respect to y. So, x power n is constant as it is, and g prime y over x, and the derivative of y over x with respect to y, that is 1 over x, which is here. Now, if we add the two after multiplying the first one with respect to x and then here with respect to y, what will happen? So, here we have multiplied with respect to x. So, n x power n, here y x power n minus 1 g prime, and then here we have multiplied by y. So, y x power n minus 1 and g prime y over x. Now, you can see that y x power n minus 1, y x power n minus 1, these two gets cancelled, and we have n x power n g y over x, which is f x. So, this is here is f x, this is f x y. So, this expression is n into f x y or n z. So, we have this result that x partial derivative with respect to x, y partial derivative with respect to y is equal to n into z. So, suppose we have this problem u is equal to tan inverse x cube plus y cube over x minus y, and x is not equal to y, then we show that x del u over del x plus y del u over del y is equal to a sin u. So, we have this sin u. So, to prove this, it is not difficult, because but one thing we have to observe that this tan inverse x cube plus y cube over x minus 1 is not an homogeneous function. But if we take this tan to this side, so we have tan inverse u, then this right hand side will become a homogeneous function of x and y. So, here we have z is equal to, so we assume this like z is equal to tan u, and from here what we have, tan u is x cube plus y cube over x minus y, and this is a homogeneous function of order 2, because if we take here x cube common, we have 1 plus y over x cube, and here if we take x common, then we have 1 minus y over x. So, this is a homogeneous function of order 2. The Euler's theorem says that x del z over del x plus y del z over del y is equal to 2z. So, we can apply this Euler's theorem on this z, on this tan u function. So, if we apply that, what will happen? So, we have applied this Euler theorem, the result says 2z. Now, this z is equal to tan u we can substitute here, because z was a homogeneous function of order 2, therefore, this 2 has come there, 2 into z. So, if we substitute now z is equal to tan u here. So, x into del z over del x. So, z is tan u. So, with partial derivative with respect to x will be sec square u and del u over del x. Then we have y, and again same situation here, sec square u and del u over del y is equal to 2 times z, z is tan u. So, now we are back to u again, u x and y, which was originally given, and now we simplify, because sec inverse sec square u we can bring to the right hand side. So, this is tan u, and then it will be multiplied by cos square u. So, here we have sin u and then cos u, because one cos u will get cancelled with that cos u. So, 2 times sin u cos u, that is sin 2 u. So, this is the result we want to prove. So, here we have used the idea that this is an homogeneous function. So, we applied that Euler's theorem on tan u, and then after this back substitution we got the result in terms of u and x and y. So, this Euler's theorem which we have seen was just a relation for the first order derivatives, but there is a extended version where we can see the second and third order derivatives as well. So, we will restrict to the second order derivatives. So, that result is x square, the second order partial derivative, then 2xy for the mixed term and y square for del 2z over del y square, and the right hand side we have n into n minus 1 into that z. So, that is the result. Now, instead of n z we have n minus 1 z, and the left side we have this expression. Well, so we do one problem on this, and this is the last problem. So, z is equal to x y f y over x, and we have g y over x. F and g are 2 times differentiable function, that is also given, and we want to evaluate exactly that left hand side of the Euler's theorem we have just seen for the second order derivative. But we have to realize that z is not a function, is not a Euler, is not a homogeneous function, but individually this and this, they are the homogeneous function of different orders. So, if we write z as u1 plus u2, where the u1, the first function is x y and f y over x, and this is a homogeneous function of order 2. Why this is a homogeneous function of order 2? Because x, and if we multiply by x and divide by x, so there will be y over x here, and f again y over x. So, this is x square into some function of y over x, let us say g. So, therefore, this is a homogeneous function of order 2, and the second function u2, this is just x power 0 here. So, this is a homogeneous function of order 0. So, in both of them we can apply that Euler's theorem, but not on z. Well, so this is the situation. U1 is a homogeneous function of order 2, U2 is a homogeneous function of order 0, U1 is given here, U2 is given here, and Z is U1 plus U2. So, Euler's theorem we can apply on U1 and U2. So, on U1 if we apply the Euler's theorem, the result says n minus 1 into U1. So, n is 2 there. So, 2 into 1. So, this is 2 U1. We can apply on U2 also, but that result will be 0 because n is 0 there. So, del 2 U2, and so we have these two separate results when we apply the Euler's theorem on each of them. And now we can add basically the two equations, because this operator, the differential operator is a linear one. So, x square, and these two will be added. In fact, del x2 we can apply on u1 plus u2, that is the linearity of the operator we will apply here. So, del 2 over del x2 u1 plus del 2 over del x2 u2, this can be written as del 2 over del x2 on u1 plus u2, and u1 plus u2 is u. So, here when we u1 plus u2 is z. So, when we add the 2 here, what we will get x square del 2z over del x square, we will get 2xy del 2z over del x del y, we will get here y square del 2z over del y square, and the right hand side will be 2 u1, and the u1 is f here xy f of y over x. So, this is the result when we apply that Euler's theorem on u1 and u2, and at the end we by adding the 2 we got actually on z. Well, so just to conclude, we have gone through the composite functions where several variants were discussed. Mainly the z is a composite function of t. So, z is given as a function of x and y, and x and y both are functions of t. We have seen that this formula is applicable to get the derivative of z with respect to t. We have also seen that when z is a function of x y and x and y both are functions of u and v, we can get partial derivative of z with respect to u and partial derivative of z with respect to v. We have also seen that z is a function of x only, and x can be a function of u and v, or we can have more variables there, x can be a function of u, v, w, and so on. So, in this particular case we can talk about del z over del u and del z over del v. So, all these chain rules we have different possibilities, some of them we have looked, but it is a easy extension for any situation we have in hand. Then the functions those were defined implicitly. We have also seen the formula that we can get dy over dx in terms of the ratio of the partial derivatives of the function f with respect to x and y. In case of z is a function of x and y, again we can get the partial derivatives also with respect to x and y of this z in terms of these ratios of the partial derivatives of f with respect to x and z. And at the end we have gone through the Euler's theorem, which was given in two different versions, for the first derivatives and for the second order derivatives. So, with this we have here the references which are used for preparing this lecture, and I thank you very much for your attention.